So finding the charges from the periodic table themselves, you know how to do it and kind of figure this one out. Let's kind of take a look at the periodic table, and we're going to write down the charges for each one of these elements. Let's start with lithium. Lithium has a positive 1 charge. What about sodium? Remember sodium? We've done that. Also a positive 1 charge. Anybody venture to guess what potassium would be? You're right. Also positive 1 charge. Are we onto something? What about rubidium, cesium, and francium? The other 3 in there. Well, we can do one more. Are we onto something? You're right. They probably all +1. What about the next group? Going down this beryllium, magnesium, calcium, strontium group. What was the charge? We can do a +1 here. Beryllium is a +2. Oh, that's interesting. What would be the charge, the valence of magnesium if you did that? Oh, wow. Calcium, we already know is +2. Oh, strontium was +2 as well. Wow, we are onto something here. So every element in group 1 has a positive 1 charge. Elements in group 2 have a positive 2 charge. Well, there's a problem though. I call this the canyon down there because we're dropping down all of a sudden, have a whole bunch of nothing. But if you skip the canyon for a minute and kind of start over at the other side, we now see, oh, these have a positive 3 charge. Look at that. This is interesting. And you can also, with the dot method, they have 1 dots, they have 2 dots, they have 3 dots. What would those have? 4 dots. What would their charge be? Well, either or. So these ones are ±4. And then as here we're starting to gain, we actually gain, so this is our teeter-totter right there, we're starting to gain electrons, and we're creating negative charges. So nitrogen and phosphorus -3, oxygen and sulfur -2, fluorine, chlorine, bromine, iodine -1 each. And here we would have a 0 because these are my noble gases or noble elements, and they are already fully occupied. They don't like to react. So we got a really interesting pattern here if we consider now the groups they are in. Just to make it really, really easy for right now, in this pattern, it works well as long as we skip the canyon. All the elements in the canyon down there, they're a little funky. They don't follow this pattern necessarily. They have multiple valences. For example, iron can be either +3 or +2. So they don't play by this really, really simple pattern. It doesn't play out too well. But as a quick reference, the groups define our charges. And that can become very, very practical. And let's skip the canyon there for a while. What about naming these compounds when we put them together? How do these names work? Well, all compounds have a first name and they have a last name. And naming starts with the first name is usually the name of the metal that's involved in that reaction making this compound. In the case of sodium chloride, sodium is mentioned first as the metal. And the last name is the nonmetal, or the anion, with IDE kind of attached to its end. So in the case of NaCl, it's sodium chloride. Chlorine would be the element that reacts, and chloride would then be the compound. So as we use that pattern, we can, for example, draw a chemical symbol, a K and a F together. Now we need to figure out what was K again, potassium. F was fluorine. To name that compound would be potassium fluoride. We can try that the same with CaO, calcium and oxygen. That would be calcium oxide, because calcium is the cation, oxygen is the anion in our little game here. NaBr, sodium and bromine. How would I write this one? Well, sodium is the first name, last name is bromine, not bromine. We need to change this to an IDE, bromide. So that would be sodium bromide. ALN, that's going to be a mouthful. Aluminum and nitrogen. Aluminum nitride. There you go. So naming, very simple process, putting things together. Now, how does this stuff make compounds? Let me run through that little parameters. Remember, they have charges. Sodium, we know, has a positive 1 charge, and chlorine had a negative 1 charge. They attract each other. One is positive, one is negative. And we need to make sure that these charges cancel out when they meet. And does a +1 cancel a -1? Absolutely. So we just need to push them together, and we get NaCl, sodium chloride in this case. That was easy. That was the fairly simple ionic compound that we are making. All right, sodium chloride is its name. Let's try something else. Remember, charges must balance. We do more with balancing later. Make some more compounds. Here we go. Calcium and chlorine. Of course, we turn them into ions. Let's look at the charges here, or valences. What is the charge for calcium? It's a +2. What was the charge for chlorine again when it makes an ion, an anion? It's a -1. Oh, we got a problem. These charges do not balance. So what does that mean? Well, that means is we need to come up with a little trick. We're not stuck. But remember, when reactions happen, when these combinations happen, it is not just a single atom reacting with another single atom. We have a pool of endless or almost limitless calcium ions, and we have a pool of limitless chloride ions, and therefore we can, if this happens and they do not cancel, we can borrow another atom. Okay, let's borrow another Cl. Here we go. We have one Cl and another Cl. That's a -1. This is a -1. You have a +2. If we push that all together, would the charges balance? Absolutely, they would. Here I can sort of check it out. How many calcium atoms do I have? I have 1. And how many chlorine or chloride ions do I have? I have 2. And we're going to put little subscripts down there of how many of those we have. 1 calcium, 2 chlorine or chlorides that are reacting. And by convention, we never write the 1. If it's 1, it's kind of assumed, we leave it off. But if there's more than 1, we write it down as a subscript. And so what we are making is CaCl2. That would be the actual compound. Name it, calcium, and chlorine becomes calcium chloride in this little example here. So charges need to balance. We will do some more balancing, little balancing act a little later. So making ionic compounds, the formula and the naming. Let's try this one. If we react potassium and fluorine, first of all, we find the oxidation numbers or the valences. Potassium is a +1. Fluorine would be a -1. All right. Do the charges balance is the next question. Yes, they do. All we have to do is push them together. Third question, what's the name? Potassium fluoride. Okay. Here, do some more by name. Can you make or write down the chemical formula for sodium nitride, calcium sulfide, and magnesium oxide? We're doing it the other way around. Okay, Let's give it a shot, see what you got. Sodium nitride. Well, these nitrogen ion had actually a -3 charge, and my sodium had a +1. So I need 3 of those to kind of cancel those -3 out, and it becomes an Na3N. It's an interesting one. Calcium sulfide, -2, +2, fits together, just CaS. Magnesium oxide, very simple too. +2, -2 for the 2 is MgO would be its solution. All right. Now I have a little bit true-false questions for you. I'm going to give you a compound and give you a few seconds to decide if this compound is actually possible or if that combination is written wrong because the charges wouldn't match. So let's give it a shot. Na2O, is that true or not? Give you a second to decide, and the answer is yes, that is true. Sodium has a +1 charge, oxygen a -2. Need 2 of those to cancel that one out. Here, I get another one for you. ALO, correct or incorrect? Okay, ALO, that one, believe it or not, is false because aluminum has a +3 charge, oxygen a -2, and so to balance everything out, you need 2 aluminums and 3 oxygen, +6 on one side, -6 on the other side, and actually the correct answer would be Al2O3 if you put aluminum and oxygen together. Let's try another one. CaO2, correct or incorrect? All right, the winner here that is false as well. Calcium has a +2 charge, oxygen -2, so you need only 1 oxygen to sort of stick together with 1 calcium, so CaO would be the correct answer. Here's Ki. Ki, is that a correct compound or some that doesn't quite work? Potassium and iodine. And the answer for that one is true. Potassium is a +1 and the iodine is a -1. All right, let's try this one, BCl2. Oh wow, I need to look it up and see if that matches at all, whether true or false. Yeah, well, remember what Cl was? It was a -1 for Cl. Boron, on the other hand, oh, that is a +3, so it should be a BCl3. That would be the correct answer for that one. Okay, what about Ba2O2? All right, this is a little tricky because you don't have to double up. I mean, it's really BaO. Barium has a +2, oxygen a -2, just need to push them together. So writing it like this, well, yeah, the charges do balance, but that is the incorrect compound because you don't have 2 bariums reacting at the same time with 2 oxygens, kind of making this square dance here. It's really 1 barium with 1 oxygen, so that is actually incorrect. Okay, now for us, it is very important in the geosciences to understand something about polyatomic ions. What are polyatomic ions? These are ions that are not on the periodic table. You won't find them there because there are two anions already combining to make another anion. Let me explain. I'm going to have a polyatomic ion, more than one element. They do have a charge, and they do have a name. All right, let's introduce you to the most common ones we find in nature, in water, as well as in rocks and minerals. So here's one, NO3. You can see it consists of a nitrogen and 3 oxygens. They're kind of lumped together. This is not neutral. It actually has a charge. It has a -1 charge, and we call this one the nitrate ion. It's a polyatomic ion with a charge of -1. Another common one is this one, SO4, 1 sulfur and 4 oxygens. It's also not neutral. This one actually has a charge of -2, and we call this one the sulfate ion. And we're going to revisit this often because it makes all kinds of natural occurring compounds. Another one very, very big in geology and in geosciences is CO3, a carbon and 3 oxygens put together. It does have a charge, also a -2, that whole blob does. And it is the so-called carbonate polyatomic ion. Okay, these are really one of the more common ones. I have one more. It's not as common, but it interacts with our geoscientific material. The PO4, 1 phosphorus, 4 oxygens being put together. It has a charge of -3. And it is this so-called phosphate polyatomic ion, also common in nature. The last one is kind of odd that I have. It's the NH4, 1 nitrogen, 4 hydrogens surrounding it. That one has an odd charge. That one is a +1 charge, acts like a +1, and it's called the ammonium ion. And that is the only, well, in that group here that I've shown you, this one is the only cat polyatomic ion, polyatomic cat ion. The other ones are all anions. So it does happen in nature, NO3 and NH4, more with organic type compounds, and these are often in inorganic compounds like minerals or ions that wander around in water. Okay, so that is our one positive polyatomic ion, kind of not fitting quite into the system. All right, how do we make ionic compounds? One more time. We have an ionic reactant, we have a formula, we have the name. So let's work with polyatomic ions. In this case, calcium and the sulfate ion, putting it together. Well, we need to look at the charge. Calcium is a +2 and SO4 was a -2. They cancel out. We put them together. We get a CaSO4, and the name of this one is calcium sulfate. Right? Let's try this again with sodium and the nitrate polyatomic ion. Let's look at this one. Sodium is a +1 valence. The nitrate polyatomic ion is a -1. Piece of cake. We push them together, NaNO3, and that would be sodium nitrate. What about barium and NO3? Okay, now it gets a little tricky. Barium has a +2 charge, and my nitrate, as we know, has a -1 charge. Oh, these charges don't balance. So I need more than one of those. But how do you write that? Well, now it gets interesting. We're going to write the whole blob, NO3. We put it in parentheses, and then we put a subscript of how many of those we need behind it. So you need 2 NO3s to cancel out the charges of one barium. So Ba NO3 times 2, or 2 of those. The name of that one would be, you could theoretically write it as BaN2O6. It's not wrong, but then you cannot easily see the name that goes with it, which would be a nitrate. I like to write it this way because then I can immediately see, oh yeah, it's a nitrate. NO3 has an NO3 group, so it would be barium nitrate right there. Okay. Making compounds, a little bit about oddball naming. When a metal has more than one charge. Now we're going to dive into the canyon. There are certain metals who have 2 or 3 or sometimes even 4 charges that go together. The canyon of the periodic table. And there are 2 naming methods for those. One is called the stock naming method, and the other one is called the common name naming method. What's the difference? With the stock method, we indicate which ion using the charge in Roman numerals. So we name it, for example, FeCl2 would be iron 2 chloride because that iron has a valence of 2. So iron 2 chloride. That's a positive 2. That would be a negative 1. And that is the so-called stock method. We'll put it into Roman numerals behind that metal that's reacting. The common name method is a Latin name method. So when we use a Latin root, what we're going to do is we add OUS for something with a lower charge and IC for something with a higher charge. It works best if my metal has only 2 possible charges that are most common. If you have more than 2, then it gets a little bit arduous to kind of figure this one out. But let me explain this one. For iron, it's fairly simple. FeCl, which does exist, is a ferrous. Ferrous, the lower charge. Here in case it's +1, and that is -1. That would be ferrous chloride. However, if it has a higher charge, is a +2, it would be actually, sorry, there's a subscript missing. It should be FeCl2. Yeah, I need to fix this eventually. So if you copy the page down, draw a 2 right there. I forgot the subscript. I apologize. It's actually a +2 charge, and then these have -1 charges. But there's also another form of iron chloride that exists with a +3 charge. You need 3 chlorides to cancel that one out. And this is a higher charge, therefore it's called ferric chloride. So higher charge, ferric chloride, lower charge, ferrous chloride. If you would use the stock method, that would be iron 2 chloride. And this would be iron 3 chloride with the stock method naming. Right? So I'm going to give you some compounds and some examples. Here's the stock method name. Here's the common name. Here's iron and fluorine reacting together with iron 2 and iron 3 fluoride, or ferrous fluoride and ferric fluoride. We did iron. Mercury is another one of those that can come in 2 valences, +1 or +2. So in this case, it's mercury 1 bromide or mercurous bromide. And this is mercury 2 bromide in the stock method, or mercuric bromide in this case. All right, some more ionic compounds. Let's do those. Let's try the following, see if we cannot figure it out. Put them together and see what you can come up with. Of course, we need to look up a little bit about copper and what type of valences they have. And copper can actually be a divalent +2 or monovalent variety of a cation. And my CO2 is stuck with a negative, CO3 is stuck with a -2. So let's see what 2 compounds would you basically write down. and name them. Right? Would they look different, and would they have different names? And they do. Let me give you the solution here. It's either Cu, CO3, that would be the first one, +2, -2, just push them together. Or in this case, if it's a valence of +1, you would need 2 of those to cancel the -2 charge, and it would be Cu2, CO3. So the first one here would be copper 2 carbonate or cupric carbonate. And the second solution with the lower charge, the +1 charge, would be copper 1 carbonate or cuprous carbonate. Okay, let's try this from the name. If I give you the name iron 3 oxide, what would the formula look like if you had to write it down? I'll go backwards. So iron 3 oxide. Well, iron 3 would had a +3 charge. Oxygen, of course, is always -2. So let's write it down. That would be Fe2O3. Right? How come? Well, I need 2 of those +6 total to cancel out -6 on the other side. Often if you have a +3 and a -2, sometimes all you need to do is switch the valence to the subscript in opposite directions, and then you get the answer. Stannic sulfate. Okay, stannic sulfate. What does actually tin come into? Stannic would be a +4. How do we know this? Well, sometimes you have to look it up. So it's a +4, and we got a -2 on the other side. So what you would need to do is an SN SO4 2 times would be the correct formula. Okay, can you do it? If I give you a name, can you write the correct chemical formula? We practiced this a little bit. I'm giving you a whole bunch of names. Let me just go through them a little bit. That was fairly simple. NaCl, we've done it several times. Ammonium, remember, is the polyatomic ion that has a +1 charge. So ammonium nitrate is NH4NO3. Ammonium oxide, you would need to put this one into brackets. A bicarbonate is an ion we haven't talked about before. It's actually an HCO3. That's a bicarbonate ion, and it has a charge of -1. So in this case, it pushes together very nicely. Malox, a aluminum hydroxide. Hydroxide is a OH polyatomic ion with a charge of -1. And so in this case, aluminum has a +3 charge, and you need 3 OH, which each have a 1 minus to kind of balance out the charges. Now hydroxide against sodium hydroxide, what is Li? That should be fairly simple, NaOH. Aluminum phosphate, you should be able to do that. Phosphate ion we had is a polyatomic ion with a charge of -3. And in this case, AlPO4 is the correct answer. Just push those two together since aluminum has a +3 charge and PO4 has a -3 charge. But if aluminum phosphide, that is your phosphorus all by itself, you should be able to extrapolate what the charge of phosphorus might be. And again, it's a -3 charge. Aluminum has a +3 charge, and it would be an AlP, would be that compound. All right, let's try one of those polyatomic systems with a valences of an element that has 2. Ferrous phosphate, what would that be? That gets rather long. What is ferrous? Is it the +2 or +3 variety? OUS is the lower charge of the two, so that would be the +2. Phosphate is a -3. Oh my goodness, it would be Fe3, PO4 in brackets 2 times. That would be ferrous phosphate. If I do iron 3 phosphate, that would be the Fe with a variety of 3+, and PO4 has a -3. You just push them together and you get an FePO4 in this case. Okay, so a little bit about how we put things together. Now, bonding. How do we bond? What we talked about when we give up an electron or gaining an electron, we call this often ionic bonding, but there is what we call covalent bonding, subtitle greedy atoms. So what is covalent bonding? Covalent bonding is where we share the electrons. We don't give them up. Sodium doesn't say, here, chlorine, you can have mine. I don't need it. I'm happy. This is among elements who say, wait a minute, I'm not giving up anything. You can borrow it, but I want it back. All sort of what they're doing. So sharing of electrons. Two atoms share one or more pairs of valence on the outermost shell again. So the outermost shell is important. This is where the sharing comes in. And we're going to use an example, water. So here's my hydrogen, right? Let's use the dot method of how many dots would you draw around hydrogen? Again, how many electrons does it have in these last occupied electron shell? For hydrogen, it's a piece of cake. That's only one shell, and its atomic number of 1. There's only 1 electron. That gets 1 dot. There it is. No more. You cannot even draw 8 around it. It just has 1. This is 1 electron. What about how many electrons could hydrogen hold if it would fill up everything on that electron shell? Remember, this is the first shell in period 1, and the first shell in period 1 can hold only 2. So there's one hole, one possibly occupancy that is allowed in this case. All right, let's answer the same questions for oxygen. How many dots around oxygen? Well, we've drawn it before. Is my oxygen. I have to draw 6 dots around there. How many holes do I have? Or how many electrons could take oxygen on if it wanted to, if it got it from somewhere? Well, there are 2 holes, right? Okay, so this is what we got. Hydrogen is 1 hole. Oxygen is 2 holes if we draw it like this. So let's take a look. Let's build a water molecule. So the electrons of hydrogen are shared with oxygen, and the electrons of oxygen are shared with hydrogen. How would that work? Let's take a look here. This is my oxygen, has 2 holes. I bring up 1 hydrogen right there, and my red electron from the hydrogen would fit in this hole, and this black electron from the oxygen would fit in this hole. So again, hydrogen would have 2. If this exchange could happen, it would be happy as a lark, looking like helium. And oxygen, of course, would have, in this case, well, 7 needs 1 more for the 8 to be full. Let's grab another hydrogen and do the same thing. We can see what happens. We exchange the 2. So let's draw this as a whole. And here we are. Here are my shared electron pairs. To distinguish them, I've colored the hydrogen, the electron that came from the hydrogen red, and the electron that came from the oxygen black. And you can see the nice sharing. Now, if I count all the electrons that go around the oxygen, I have 8. Oxygen is happy. All the electrons that go around hydrogen, there are 2. Hydrogen is happy, and we're in the sharing mode right there. This type of bonding where we share is called covalent bonding. And this is how it happens. We really are sharing these electrons. between other atoms that react. Okay, a little bit more about covalent bonding, something about the chemical gas rules. All non-noble elemental gases appear or create pairs in nature. These are the elemental gases, not the polyatomic gases like carbon dioxide. They come in pairs. So what does it mean? Oxygen actually exists as O2 in the atmosphere, not as single O. Nitrogen exists as an N2 in the atmosphere, not as a single N. Fluorine, for example, would be an F2. Chlorine gas would be a Cl2. So this is how they actually would appear in nature as what we call a pair of these gases. H would come as an H2, for example. Okay. But why is that? Well, this is the story of what we call the free radicals. What would it be like to be in an atmosphere that is composed of a single oxygen atoms? Let me say it this way, you wouldn't survive. Why? Because a single oxygen is absolutely reactive. Matter of fact, to make an O2 react or to burn or even in your cells, it has to be ripped apart in two single O's because the single O will make the reaction. We call this, when this happens in the body, a free radical. And it immediately, if it's a single O, will react with whatever it comes in contact with. It won't even wait. This is why in the medical or health world, you often see free radicals are bad for you. This is when this O2 kind of splits up inside your body. That's not good. We can take it to our advantage. There's a compound out there. It's called hydrogen peroxide. Its chemical formula is H2O2. And when you put it in contact with any surface or anything actually, it falls apart into water, H2O, and one free oxygen, one O. And that oxygen will react immediately with what it comes in contact with. This is why hydrogen peroxide is such a powerful disinfectant. It basically oxidizes whatever is in its way. And it works really great on a lot of things. Okay, so here's one of my what do I have here? That looks more like a chlorine or fluorine. Can't remember. One of those. You need another one, and we need to stick them together to share these electron pairs to make these paired non-elemental gases. So, what's the difference between covalent and ionic bonding? Right? In short, materials that usually dissolve in water are more ionically bonded. Well, salt is a perfect example. It dissolves in water. Anything that has an easy time dissolving in water usually has an ionically bonded structure. And stuff that doesn't dissolve in water, or not readily at least, is more covalently bonded. So that's your quick test. Does it work all the time? No, but it works often enough that it gives you a good point there. All right, so let's look at the charges and the ionic versus the covalent bonding a little bit. And here you go. Most of this side here has a tendency to ionically bond. Most of this side has a tendency to covalently bond. So an ionic bond makes compounds. There is a transfer of electrons. Either you gain one or you lose one. It is a combination usually of a metal and a non-metal. Ionic compound is composed of positive and negative charges. It's actually a fairly weak bond. That's why it dissolves in water. And salt is a good example, NaCl. On the other hand, the covalent bonding actually doesn't make compounds, it makes molecules. It shares the electrons in order to kind of hit the noble column. It is most commonly made out of nonmetals. It is neutral when you throw it in water. Their bond is fairly strong, very difficult to rip apart, and there's all kinds of compounds that fall into the covalent category. The little list here. So, another can you do it? Try to draw the covalent bond models for the following 4 reactions and show how these electrons are shared. Remember, we did it with water, and we showed it to you on that chlorine gas molecule. So let's do 2 hydrogen atoms, 2 fluorine atoms, reacting carbon and oxygen, and reactant carbon and fluorine. Okay, shall we give it a shot? See what you got? At least some of them. Here are my drawings that I have. 2 hydrogens, they shared right there. My 2 fluorine atoms, you got the share point right there, all 8 around it. 2 oxygen atoms and 1 carbon atom, they kind of do this little number. It was hard to draw, you need to stretch it out to this end. And if you have 4 fluorine atoms and 1 carbon atom in the middle, that's much easier to draw. You see it right there, kind of making sure that we share this one. That was tough, and I should have put this one on this side, made this ring really, really big for the carbon to give it a visual. Somewhat difficult to draw these visuals sometimes. Okay, so much for making chemical compounds. There's another way of working with covalent bonds, and that is the so-called ARM method. I'm going to introduce you really quickly to this. What's the ARM method? There's an easier way to show covalent bonding in drawing these dots and see what is shared and what's not. We're going to use the ARM method. What is the ARM method? Well, believe it or not, the elements of periodic tables have arms and they can hold hands. Ha! The rule is no arm can be dangling free to do that. All right. How do we figure out how many arms an element can have? Well, an element can have only 1 arm. They have 2 arms. They have 3 arms. It's hilarious when you do this in the classroom because I ask students to build these by pretending they have 3 arms, and they will use 1 leg and 2 arms, and they have to hold on to another student and make all these compounds. It's kind of hilarious. But we're going to try this by just drawing. So how many arms does an element have? And that depends on what it is. Each dot and hole, dot X pair in the last electron shell configuration equates to 1 arm, makes 1 arm. So let's try it. How many arms do the following have? I'll show you on an example. So H, what is my dot and hole configuration? If I drew this one, has 1 electron in the outermost shell, but can take in 1 more. There's my dot and X pair right there. And therefore, hydrogen would have only 1 arm. That's my pair right there. That's how I would draw hydrogen. Hydrogen was 1 arm. There we go. What about oxygen? Okay, if we drew the dot model again, I have 6 electrons around there. Remember, I'm spacing them out. So I start here, 1, 2, 3, 4, 5, 6. That leaves me with two holes right there. I get 2 dot and X pairs. And so oxygen, therefore, would get 2 arms, would look like that. I think that's fairly simple. Give you the idea here. So can we make water now? That would be easy. So what we're going to do is we draw the oxygen, and each of the arms of oxygen holds hands with one of the water molecules, and there is your covalently bonded water. Just saying. Fairly simple, straightforward method to do these covalent bondings with the arms. So how many arms would you get if there would be covalently bonding involved? I'm going to go through some elements. We're going to try nitrogen. Nitrogen, if I drew this one as a dot method, I would come up with 3 dot X pairs, and therefore I would generate 3 arms. I would like to draw this out with a nitrogen using the dot method. Have a dot X pairs, 3 arms. Fluorine, well, there's only 1 dot X pair because what we're having is 7 electrons in the outermost shell and 1 hole left, so it gets only 1 arm. Poor thing. I have a few more. What about boron? Again, how many dot X pairs I can have. By the way, you can draw it and have a lot of X's around it, but we're looking for dot X pairs, and actually it has also 3 if you would draw this one out as boron. All right. Sulfur, again, if you drew your dots around there, look for the holes as well. Sulfur has only 2 dot X pairs that are left. Right. Silicon. That silicon is interesting. Remember, when we drew the dot or talked about valence, could be a +4, could be a -4. Well, silicon actually ends up with 4 dot X pairs and has 4 arms that it can hold on to neighboring things. And carbon. I'm going to give carbon a shot. Carbon is in the same boat as silicon. I'm going to end up with 4 dot X pairs. And this is what I would get, a 4-armed carbon as well that can hold hands with other things. Right? Aluminum, if it would make a covalent bond, how would this work? Well, how many dot X pairs do I have? I have 3 dots around aluminum in the last electron shell, but I have a lot of X's, and I would end up with 3 dot X pairs actually, and I would give aluminum 3 arms in that whole mess right there. Okay, let's do one more. Chlorine, 7 electrons, 1 hole, gives me 1 arm. And I can put them together, and they can do all kinds of crazy hand holding. All right. Covalent or ionic bonding, how do we know this? Is there any way to figure this one out? Well, they created a table. It's called the table of a periodic table, basically. And it lists funky numbers. These numbers are the numbers of electron negativity. It's something they measured. And what is electronegativity? Electronegativity is the likelihood of attracting a shared electron. So with other words, the higher the number, the more likely it is for them to kind of grab an electron from somewhere else and hold on to it. So fluorine is a winner. There's almost 4. It kind of grabs all the electrons it can. Lithium, on the other hand, is a lame duck with only 0.98. It says, yeah, whatever, take my electron, I don't care. All right, and then we have this other funky table that tells the difference in electronegativity between the elements that react with each other and what the percent of ionic bonding would be. So let's try this on a few things. Let's do table salt halide. Halide's chemistry is NaCl. So we have a sodium involved and a chlorine involved. Let's look up the 2 electronegativities. Chlorine has an electronegativity of 3.16 right here, and sodium of 0.93. We take the difference. Basically, we subtract the lower number from the higher number, and we get a difference, which often is described as delta, of 2.23. Now let it go to my little table up here, 2.2, 2.0123 right here. So table salt has roughly 74% ionic bonding. There it is. Anything over 50 we usually call ionically bonded. So halide, the mineral halide, which is table salt or sodium chloride, is indeed an ionically bonded material. Now, there's really hardly anything in this world that's 100% covalent or 100% ionic. There's usually a little bit covalent bonding going on with any ionic bonding, and there's a little bit of ionic bonding going on with everything covalently bonded. So let's try another little example. So this is an ionically bonded compound. It's over my 50%. What about water? H2O. Okay, let's forget about the subscript for a minute. Here is my oxygen, 3.44 again. And I need to subtract the hydrogen, and I ignore the subscript there. My hydrogen is 2.1. I'll put these ones, subtract the, again, lower number from the higher number, and I get a difference of 1.34. Okay, up to my table, 1.3 is right there. And what I'm seeing is it's only 34% ionically bonded. So water would be indeed a covalently bonded compound. So this is the mathematical approach. Our quick test is to throw it into water and see if it dissolves or not.